I'm gonna try to put you on the screen, and so sometimes it switches back and forth, wherever the volume is the loudest.
Yeah.
Oh, I think I see you guys. Hey, you guys. Hey. How's it going?
Good.
That's it.
They're eating their lunch a little bit.
Hey, that sounds good to us. We're eating lunch too.
We're trying to get you up on the big screen, so give us just a second here. I got the video going, but the big screen's no bueno.
Okay. Hey, Mr. Powers.
Hey, how's it going, guys?
Good. How are you?
Just trying to get this thing squared away. Hold on a second.
Okay.
What is it? Okay. Alright.
I don't know how to get this set so you guys can see them. You guys might maybe pull your chairs closer.
Like get behind us. Yeah. Okay, we'll split apart a little bit. So somebody put it right here. Okay, there we go. I don't really want the one to front.
We don't see your picture yet.
Yeah.
Oh, there's Mr. Powers.
His beautiful face, right? Next, big.
This is getting awkward.
Who's making it so?
I don't know.
I was telling her that she
No,
that's where it should come out. It's right there.
We might have to do it without it.
I heard so.
Okay. Okay. So we do not have the big screen, but my students are here. Can you see them?
There we go. Got some waves.
Can you see them?
Yeah, we can. Yeah. Yep. You're small though. Do you know how to make them big?
It's whoever's talking is the
Oh,
loudest.
okay.
Whoever's the
There we
loudest
go.
is
We're good.
the one up front.
We're good.
Yeah. They're naturally smaller than you. They're fifth graders.
Yeah. Yes. Okay.
So,
Well, you know, we have your list of questions, and we kind of tried to type up some answers because I got to be honest with you. When we were looking through those questions, those are pretty advanced questions. Yeah. That's stuff that it's a lot of theoretical research, a lot of things that are above our head that we don't study in high school at all. So we did our best to kind of put some notes together on how we could best answer these questions and try to make it at a level that we understand, and hopefully you guys understand too.
are you guys hearing him?
Yes.
Okay.
Okay. All right. So I thought maybe we could start right off at the top. Which one of you want to talk about atoms? You're up front. You talk about atoms.
Okay, I'll talk about atoms. Are we just going straight off the
Just
questions?
to read their question, and then we'll go through a few of those and see how we're doing on time.
Okay. So,
Say your name too.
alright, I'm CJ. So, do atoms give off any taste or smell was the question. And the answer to that question is that they don't. Atoms are a really small particle that you can't actually, like, I don't know how to describe that.
Well, they make up the
Describe atoms and
compounds, and
Yes,
the compounds are what?
Okay. So they make up different atoms work together to make up different compounds that would produce the smell. So it's not the atoms that's giving off the smell,
Right.
kind of.
Right. And of
Weird
course,
concept.
when you're smelling, it's really just your brain interpreting electrical impulses. So I don't know if that makes a lot of sense, but so atoms themselves don't have a lot of the properties you might be thinking of.
Okay.
Okay.
Be loud. I can hear you.
Okay.
Okay. So good. All right. So what about now? We're gonna
What is this?
we're having a Miss DeMaria. This is Miss DeMaria. She teaches chemistry at Rocklin High School too. This is Rocklin Elementary School, 5th grade. They had some science questions, so we're having a Google Hangout.
Oh, fun.
Yes.
I have a club meeting that's about to happen. I'm
Right.
just taking my test.
Right.
Do I mind if I fill in that row
Nope.
behind
No
you?
problem. Okay.
I might have to head over there too.
Okay, that's fine. All right, so why don't you talk about gluons then?
Okay.
Gluons, that's a really hard one.
I don't even know what a gluon is.
So I would say this. You know, a big question a lot of even my students have is, why do atoms stay together with protons, neutrons, and electrons? Here, we're going to scoot this a little bit this way. Okay.
We're on the move.
Oh, there are cords, there are cords, there are cords.
Oh, there are. Why don't you guys go around the desk that way? Thanks for that heads up. So we have a lot of stuff going on in our classroom, unfortunately.
You can't.
Okay, so a lot of students have questions like, what keeps atoms together? And it's really what sometimes it's generically called the strong force, which sounds kind of silly, right? It's a strong force. But strong forces are the gluons, which is like glue. Like glue things holds together. So gluons are that force that holds those protons and neutrons together. Okay? So, but however, gluons don't really have anything inside of them. They're sort of like, they're similar to the elementary particles. Elementary particles are the smallest things that can't be divided any further. So in that case, and this will refer to some of the later stuff, but gluons and quarks and electrons, and all of those, they can't be divided any further down. So they're referred to as categorically elementary particles. So there's nothing inside of a gluon.
I got a question here. You
Yes.
sparked a question.
Then what are gluons made of?
Hold on a second.
Try to stand up and a little closer because it has to.
What are gluons made of?
Okay, Mr. Warner.
What are gluons made
What
of?
are gluons made of is the question.
There's particles. Yeah.
Gluons are made of energy. They're more of a like force than a particle almost. So that's pretty much it. So they're not like a physical object. They're more of an energy.
Would that mean that
Yes.
He said thank you.
Sure.
Okay.
Good.
Okay, but thank you.
You're welcome. Trying to talk about quarks and electrons and compare those.
Try. So question 3, what are inside quarks? Quarks, Mr. Warner just touched on that, are elementary particles, so you can't break them down any farther. So we actually don't know what's inside of quarks because they're the lowest, smallest piece. We can't break it apart. Does that make sense? That's it, right?
Yeah, and I would say this. Something that's kind of interesting about quarks is that they can't really observe quarks. They don't really study quarks. They observe the effects of quarks. So they see what happens around the quark, and that's kind of what they study. But they can't actually interact with, see, or touch with any of their instruments the quark themselves. So we have no idea. I mean, it's an elementary particle. We assume that there's nothing smaller. At this point in time, science has not found anything that is composing up the quark. What the quark is made up is just the quark.
Okay. Yeah.
Okay.
Okay. And then what's inside of electrons is next. And electrons are similar to quarks where they're a small elementary particle, so you can't break it down any farther. So there's nothing inside an electron.
Right.
Yeah, nothing inside of an electron.
Just energy.
Just energy.
Okay.
Okay.
Kind of interesting about comparing the mass or which one's bigger, quark or electron?
Yep. The electron is smaller and weighs less. I don't know how to explain why. Is there a why?
Well, you could just say this.
Why. Okay. That's a proton though.
Oh, it is. That's true.
Yeah,
Huh?
that's a proton. It's neither.
Oh, I went a little bit further. So you guys were really looking at a lot of really small things. Sorry. You guys were looking at a lot of really small things that it's really difficult to describe. They're just basic, and it's a lot of theoretical research right now. Theoretical just meaning they don't know for sure. They keep studying and hoping something comes from the research.
Okay.
Okay.
I expect these guys to actually do all
All right,
of the
CJ has to go right now, but we're gonna have somebody else step in. You guys want to, Amy or Michael? You want to sit here?
Mr. Warner, my students here, I'm expecting them to become the researchers of all those small particles.
That would be awesome. We would be very excited for that to happen. That's a huge area of research. They're hoping that a lot of future sources of energy and things can come from what they can do with atoms and on that nuclear, in the nucleus of an atom and that nuclear level. And so that's what you guys are looking at on the nuclear level, all of these particles you guys have been talking about.
Awesome.
That's good. It's really good. Okay, so then we kind of got to, you want to take on Planck's?
Yeah, so the next question was, what if Planck length got smaller? Well, Planck length is a theoretical measurement, so it can't actually be changed. I don't know what it, oh wait, it's,
Well,
what
like,
it is.
yeah, well,
Yeah.
so tell them how long it is.
It's roughly 1.6 times 10 to the negative 35th meters, or about 10 to the negative 20th times the size of a proton.
Which is really, really small. And so they have something that's that small, but the funny thing is, it doesn't mean anything. Like, they don't use it for anything. Planck length is just this really small measurement that has no actual significance at this point. I mean, they say that it does, but they're not using it to measure anything. So I don't even know what we would do with Planck length, to be honest with you.
It's supposed to be used.
We've got the giggles here now. That's funny.
Oh, no.
It's apparently supposed to be used to explain the theory of everything,
Oh.
which no one knows yet. So,
Okay. Did you guys hear that?
No.
No.
Say it again.
Well, it's supposed to be used to explain the theory of everything, but no one knows what that is yet. So, as Mr. Warner said, it's still useless.
Yeah. So maybe you guys will come up with a theory of everything. That would be really helpful.
To dance.
Yeah. Yeah. Okay. Oh, talk about. Did you read them on table salt versus other salts?
I didn't actually see that question last night.
You did?
Yeah.
Okay. Here, let's Amy sit there.
Yeah, I got the spinny chair.
This is Amy.
Hi, I'm Amy. The next question was, what's the difference between the compounds in table salt than any other salt? Well, table salt is usually sodium chloride, which is two fairly common elements, but most other salts can be any other combination of a metal and a nonmetal. So you can have quite a few different kinds of salts, and you can't eat all of them, so.
I will tell you, Amy, that today we used our 3D blocks to look at the compounds between some of our metals and nonmetals, and that was one of the questions we talked about was how what would like sodium fluoride, for example, be used for?
That's really cool. I actually went to Rocklin Elementary too, so.
Bulldogs rule, right? Woohoo!
Yeah.
So I would say this, when we talk about like sodium chloride, that's our table salt. That's what we eat most of the time. But there's other types of salts that have so a lot of the salt you eat is actually iodized salt. If you guys happen to read the side of your salt containers at home, which is kind of interesting because iodine is used to help control the thyroid gland, because there was in the 1920s they were having a lot of goiter, which is when the thyroid gland was enlarged. The thyroid gland helps control metabolic rate, and so they were using that, and it just kind of stuck around. I mean, this iodine, it's not even necessary. It's not necessary all the time, but there are countries where it is necessary. So there's iodine in a lot of salts now. But a lot of people eat things like kosher salts and sea salts, and those don't have iodine, but they might have other minerals like calcium or magnesium in them.
Okay.
Good. How about
We have another.
Hey, we have your location.
yeah?
There's such a thing as dark matter. Well, dark matter is a hypothetical kind of matter which can't be seen, but apparently has been detected before. But it's not visible, and
See, you guys were really good at asking questions about theoretical things. It's really hard. So a lot of times when we're looking it up, I'm like, okay, well, theoretically, we don't know what it looks like or what it is, but we see its effects. And dark matter is one of those. Like, scientists believe that the majority of the universe is made up of dark matter. The reason they know that is because of the gravity and the effects of the dark matter on the space around it, on planets, on stars, on galaxies. And so when you ask is there such a thing? Well, yes, there is talk about the dark matter, and if you watch a lot of science fiction, you're going to hear a lot about dark matter, but science fiction has a whole different idea of what dark matter might be. But it is there, but we don't know exactly what it is or what its exact function is. We just see sometimes what its effect is on other things around it.
Okay.
Oh yeah.
Cool. Thank you. So I kind of get it now. You think really big writers?
He wants to know if you think they'd be really good science fiction writers.
Oh, absolutely. You guys have all kinds of great ideas about theoretical things, and since people don't know about it, they love to hear ideas about it. And in science fiction, you come up with really neat ideas about the way things work, and people will totally eat that up. You should be a science fiction writer for sure.
Yay.
If you're not going to be future scientists of America.
This is also
next
true.
best thing.
Yes. Want to talk about the cells?
Okay. The next question was, when you die, do your cells continue to operate? Your cells are going to continue for a little while, but since you are technically dead, the different parts of you will be dying because you're not going to be getting oxygen to those cells, which they need to function.
Yeah, you're legally dead when your brain can't function anymore and when it loses the basic function of allowing you to breathe. So, yeah, your cells can continue on living, but it doesn't mean that you're alive. It just means that your cells are.
Okay.
Break the speed of light.
If something were to break the speed of light.
You know what? Let me take that. So you guys asked about something breaking the speed of light. The problem with the speed of light is that this may not make a lot of sense, but Einstein had a theory of relativity. E equals mc squared. You probably see this everywhere. Well, the idea behind that is that as you approach the speed of light, there's a time dilation, so time slows, and as you get closer and closer, mass grows infinitely. So if you're right at the speed of light, mass would be infinite, like how much you weigh or something like that. So it's really hard to talk about because now, again, we're in the theoretical. Like, so if you watch Star Trek, there's warp speed, which is beyond the speed of light, which at this point in time, we don't think that's possible. So there's been some research. They've talked about wave propagation and trying to get past the speed of light, and they say that it kind of works, but it doesn't really, so it doesn't mean anything. Again, I'm so sorry to say this, but so these things that you're asking, they're not really possible. So breaking the speed of light, not so much.
They're sad now.
I'm so sorry. Hey, but you can do it, the whole theoretical, and that's where, I mean, that's half of science fiction. With future science fiction is based on the idea that you can break the speed of light. Yeah. So don't feel too sad. A lot of people want to break the speed of light.
Yeah.
Okay.
Temperature.
Temperature?
Don't forget to speak up.
What's the coldest temperature or Planck temperature?
Both of them. So go, just compare them.
Questions answered?
No, I only had one.
You sit up here with me.
No, we had two. I had three. Okay, you can
Out of like
now.
25. There were 5 in all.
15.
Go ahead.
Okay, so Planck temperature is 100 million degrees, but how much is that in Celsius? And I think that would already be in Celsius, perhaps.
So what is it? Oh, okay.
Go ahead.
What is it in Fahrenheit then?
In Fahrenheit, how do you convert between Celsius and Fahrenheit?
So if you to convert this from Celsius to Fahrenheit, you have to take the Celsius temperature, multiply times 9/5 and then add 32. Yeah, the conversion to our American English way of doing it is really inconvenient and not helpful at all. So we try to stay closer to just Celsius and Kelvin. It'd be a lot easier if the United States would just switch to the metric system. We'd get we'd be able to do a lot more. But so the thing is that with converting between Planck temperature and Celsius, right? You just, because it's Kelvin, which is the absolute temperature scale, you just subtract 273. So if you wanted to convert that to Fahrenheit, after you subtract 273, you multiply times 9/5 and add 32. I mean, it's like it's not as useful. But.
Okay, you might call me procrastinator, but I'm gonna do that later, not now.
Oh, say that again?
You might call him a procrastinator, but I have to do that later.
Oh, okay. No, not at all. Did you talk about episode 0?
No, actually.
Okay.
And what's the coldest temperature matter/non-matter can get, but how much is that in Celsius? The coldest matter can get is 0 degrees in Kelvin, so that would be
Negative
negative 273?
Mm-hmm.
Yeah, negative 273 degrees Celsius.
Okay.
All right. When everything gets to 0, again, this is a theoretical temperature. Once again, everything is theoretical. You guys have asked about. So the absolute 0 motion, all matter stops moving. Everything stops moving. And so at 0, everything just kind of breaks down. That's why it's theoretical, because nothing could really exist at 0 degrees. They've tried to get down there. The closest they've gotten, I understand, is like 0.15, or no, that's the 273. I don't know. It's low. It's below a degree Kelvin, but again, it's very difficult to make it happen.
Are you sitting on Dalton?
Oh, really?
Yeah.
Oh, that's pretty.
Not all.
Okay.
You want to take different types of matter.
Okay.
So the next one caught us off guard because the 7 types of matter, we don't really study beyond the basic 3, and the 4th one we know about, well, we just don't talk about it very much. So we'll do our best with the other types of matter, but it's, again, theoretical.
We're very familiar with the wait a minute, is it solids, liquids, gases, and plasma? Are those the 4?
Good.
Yeah.
Yes.
Here with those.
We watched a video.
I should take that back. We're not super familiar with plasma.
Okay. Well, that's understandable. Well, like fire is plasma
Yeah.
because it's excitable, it's unpredictable matter going a lot of different directions.
Lightning. Lightning is plasma.
What?
Lightning is also plasma.
Oh, yeah. Yes, lightning is also plasma. You're right.
Yeah.
So the other 3, though?
We've been rapping about the states of matter.
Oh, you have? Can we hear it?
And it goes something like, we get atomic, we get down, we get elemental.
Ah, nice. I like that. You guys need to record that.
It's actually a vocabulary video.
Oh, really?
Yes.
That sounds kind of cool. We'll have to check that out. So as far as the 7 types, the other 3 that are a little more popular, they're called the quark-gluon plasma, the Bose-Einstein condensate, and the fermionic condensate. And so we've already talked about quarks and gluons. Now they're quarks and gluons together. Bose-Einstein condensate is really just it's when matter is at extremely low temperatures, and it's made of bosons, which bosons are I don't even know what they are exactly, but boson sounds kind of like Bozo the Clown to me. And then, yeah, fermionic condensates are similar to Bose-Einstein condensates, but they're made of fermions instead of bosons. Again, no clue what a fermion is. So I don't think I can help you. They're all like theoretical. So.
Please stop making us laugh.
Okay, we'll try.
Just say.
Here,
What is the weight of Planck gravity?
Michael's going to cover Planck gravity.
Well, the weight of Planck gravity is 2.17645 times 10 to the negative 8th kilograms, which I don't know how much that is in grams.
It's
I feel
pretty
like
small.
converting it right now.
Yes.
Question.
Valid
Oh, you have
question.
a question? Okay.
Would that be more than the gravity on Earth or less than the gravity on Earth?
Gravity on Earth is
9.6 times
9.8.
9.
Well, so you guys are going to give it in meters per second squared, right?
Oh, yeah.
So the thing about Planck gravity is that gravity is actually one of the weakest forces. There's like 4 main forces. We talk about the strong force that holds atoms together, much stronger than gravity. Gravity is actually considered sort of a weak force. Well, Planck gravity is the idea that you can have at that mass, which is a very small mass, at that mass, gravity might be that gravity might be enough to be strong enough to be compared to the other forces. So when you talk about gravity, gravity itself is actually it's not very strong. And then if you make something really light, really light, then it might be to the point where it's small enough that the gravity, because anything that has mass has gravity, which is why the planet that is so much bigger has gravity. We actually have gravity. We are actually attracted to other things. We're attracted to the planet. We're attracted to the rocks and trees and each other, if you want to say that. But there's all of this mass, and mass has gravity. So if you make it really small, though, now that other things aren't interfering with it, it might be strong enough to be considered one of the stronger forces. So that's the idea behind Planck gravity. Again, not using it for a lot, though.
Got it.
Okay.
That wasn't theoretical.
Let's go to energy.
Oh, energy? The next question is, can energy be destroyed? And no, that's the law of conservation of matter. Matter cannot be created or destroyed, and neither can energy.
We just had an I told you so moment.
Yeah.
That's awesome.
Yeah, but we told you.
Okay.
And I told both of you.
Awesome.
Told that.
Thank you very much.
Okay, so we're going to shift to the last set of questions you guys had about the reason you get heavier.
So is the reason you get heavier because you get more atoms? Well, technically the answer is yes, but it's mostly because you're eating food. Yeah, it's really funny. You're eating food and you break it down into its basic components, and your body uses those to build more muscle or fat, which are all made up of atoms.
I have a question.
Yes.
You gain the atoms that you eat.
Do you what?
Do you gain
Gain of the atoms that you eat.
Yes, because you're taking the food that has one molecular compound, and your body is oftentimes breaking it down to simpler forms or rearranging it and using it in other ways. And so yes, the atoms that you eat go into you and are being used by your body to build, repair, maintain.
Okay.
Okay. Do you want to talk about splitting atoms?
If you split two different atoms, then put one half, then one of the other half together, what would happen? Well, splitting atoms is nuclear fission, which results in a massive amount of energy, but results in new atoms, not a half an atom. And this happens in nuclear reactors, which is energy that we use all the time. Volts.
Can I just clarify? So when you split an atom, it creates new atoms that are very highly reactive?
Yes. Yes, and usually when you're splitting an atom, it's usually a large, unstable atom to begin with, and so there's like a chain reaction. It splits a few more times and breaks into more of the different elements. So every time it breaks down to a smaller and smaller element.
Okay.
I think I see hands. You guys have questions?
You froze for a little bit. Yeah, can you say that again?
So when an atom breaks apart, you get, so let's say you have, when an atom, like let's use plutonium as an example. If you have a plutonium atom, it breaks apart into like a lead atom, and then into like, maybe let's just say 2 lead atoms, or it breaks into a couple other elements. It doesn't split, there's not like a ball that you cut in half and have 2 different halves of an atom. It actually comes apart and you have protons and neutrons, so you have different atoms, and so it becomes a different element. It's usually still unstable, and so it breaks down a couple more times. Yes?
Does that mean that the smallest state of matter is the atom that you get from splitting an atom?
Yes. Yes, because the atoms are the smallest unit atoms are the smallest unit of an element that retain the properties of that element. So, like, the word atom actually comes from the Greek atomos, which means not able to cut anymore, basically.
But
yes.
if you cut it, then how is it still another atom? Yeah.
I don't get it.
Now, because when they first came up with this term, they didn't know that that elements were made of protons and neutrons. So, but if you want, when you keep breaking them up, you're just getting more protons and neutrons and electrons. And so as long as you have protons, you have elements, because protons are what make the elements. They're the nucleus. They determine which element you have. If you've ever seen a periodic table, it has numbers starting with 1. If you have 1 proton, you have hydrogen. If you have 6 protons, you have carbon. If you have, let's see, 88 protons, you have radium, which are they're just larger and larger elements. Yes?
You have 2 follow-up.
Okay.
Isn't the smallest state of matter if you split an atom, there are atoms there, and you split those atoms, and then you just keep doing that forever?
You could do that until you get onto 1 proton.
Oh, so is there a smaller state of matter than just hitting an atom and then more atoms? Could you just do that again until you get 1 proton?
Well, if you keep doing that splitting, then you're getting down to the quarks again. So we're back to quarks and gluons and bosons. So that's you can't. I mean, that's why they keep talking about like the elementary particles that can't be split anymore. But protons and electrons and neutrons are not considered elementary. They are considered to be able to be split into those quarks that we talked about earlier.
Okay.
I see a hand in the back.
What percent of the atoms make when you split make a nuclear explosion, or do all of them do?
I think it's hydrogen.
No. Well, I would say that there's 100 and I don't think we're up to about 117 or 118 elements, and the ones that are most unstable are 84 to 117 or whatever. So that's only about 30 or so of the 120. So maybe like 25% are really unstable. The ones though that they can use to make those explosions or be able to produce that kind of energy are not that many. The ones that are abundant to us and available to us and that can exist long enough to do that, there's probably only about 4 or 5 different elements that we use, like uranium and plutonium. I want to say neptunium. Those are the ones that we can break down and use energy or cause explosions.
Cool.
What are you planning here?
See.
I have one more question, and then we have to go.
Okay, that sounds good.
Okay.
Wait, still, I had a question but didn't make it on paper.
Okay.
Nice enough.
So, how many atoms / molecules would you have like during your whole lifetime? Would you have this amount, or like how?
That's a good question. So let's start with this. Do you know how many donuts are in a dozen donuts?
Yes.
How many?
12.
12. Good. So the way we count atoms is in a mole. So how many atoms are in a mole?
6.022 times 10 to the negative 20.
Positive
20.
23rd. Okay. That's a
that
huge number of atoms.
I'm impressed she remembered that.
So
Yes. Yeah. It's a crazy number. So that's 1 mole. So if the way a good way to so that you can get kind of a picture of that, 18 milliliters of water, which is like this much water, is 1 mole of water. So your body is made up of, and times 10 to the 23rd is, you're looking at that, remember when you're talking about that Planck temperature of hundreds of millions of millions of millions? That's the same thing here. So when you start talking about atoms over your lifetime, I don't know if we can come up with that number. That number is astronomically huge. So it's a little bit difficult because even you, like as a person, you're made up of probably millions of moles of atoms right now, and then every day you slough off atoms in your skin, in other ways, and then you ingest more atoms, and we're talking about hundreds of thousands of moles every day. And so that's over the course of your lifetime, so that's every day, 365 days a year for hopefully 80 to 90 years. So I don't think I can come up with an exact number, unfortunately, on that one. But that's a good question. It's just that the number is enormous.
Awesome. Well, Mr. Warner, thank you very much. My students are going to introduce themselves to you in case they have another question. You may hear from them.
Oh, that sounds great.
Now that they have your email address, they
Yeah.
That's a,
Mr. Warner and Amy, and I'm sorry, in the blue shirt in the back, what was your name again?
Michael.
Michael, Amy, Michael, and I think you have one more student in back there.
Yes,
She's not.
that's
He's
Brooke.
not in this.
This is Jordan, Logan. I have Dalton, Reese.
Hello.
And Seth, and Tanner is walking away. He's hiding behind me. But
Okay. Well, it's nice to meet you all.
And thank you very, very much. We really greatly appreciate it.
Oh, it was very fun for us. Thank you.
Have a good afternoon. Thanks so much, guys.
Thank you. Bye.
Bye.
See if I can figure out how to turn this thing off now.
Just hit stop broadcast. Or the hang up phone, the red phone at the top.